Hey everybody. Here we are. We're going to do example problem 8.2 from the textbook. Here we're being asked to represent graphically the fraction of these two chemicals, a total 2,3,4,6 tetrachlorophenol and total aniline, present in the water phase of a dense fog as a function of pH. And the pH is going to range from 2 to 7. And we're going to do all this at 5 degrees Celsius. So it's a cold winter day. We have a dense fog that has formed. Now, rain in general, as you know, has a slightly acidic pH, somewhere around 6.5 or so, sometimes even lower. And then when you get into polluted areas where you have, for example, coal burning that's producing sulfur dioxide, the sulfur dioxide gets oxidized to sulfuric acid and you get acid rain, right? So it's not unusual for droplets of water in the atmosphere to have pHs going down to 2. And then the idea of the fog is that, fogs form and then they will burn off, right? So what that means to burn off means that they start to evaporate. And as the fog evaporates, the water is evaporating, but the sulfuric acid, which is protons and sulfate, that's not evaporating because it doesn't evaporate. It could form a salt and become a salt crystal and become a little particle that is devoid of water and then falls out of the atmosphere, but it's not going to turn into a gas. So as these droplets of water evaporate, they become more and more acidic, and that's how you can get quite acidic pHs in your dense fog. So this is a realistic scenario. So we want to represent graphically the fraction of these two chemicals that are in the water phase in a dense fog. So in other words, we're doing a two-phase partitioning where we have air and water. And instead of having a volume of air and a volume of water, what we have is a ratio of the two. The ratio of air to water is 10 to the fifth. So there's 10 to the fifth liters of air for every liter of water. So to do this two-phase partitioning, we're going to use the same math that we've done before. We're going to have our mass balance here. I don't know where my FW went. But anyway, FW is going to be the mass in the water divided by the total mass. The mass in the water could be described as the volume times the concentration divided by the total mass, which is the mass in the water here, plus the mass in the air. And remember, we do our little parlor trick of dividing each of these terms by CW. So the CW's cancel out here, and here you get CA over CW. Now, normally we would substitute in the KAW, the Henry's law constant here, for the ratio of Ca and Cw. But because this is an acid or base, remember from the lecture on acids and bases, we're going to use DAW, the distribution coefficient here, instead of the KAW. And then the last little trick we're going to do with this equation is to divide all the terms through by VW. So you get this equation. The fraction that's in the aqueous phase is 1 over 1 plus this distribution coefficient for air and water times the volume of air divided by the volume of water, because that's what we have. We have the ratio. We don't have independent volumes. We just have the ratio. All right, so first thing we got to do is we have to adjust our Henry's law constants for the temperature change. So we're going from 25 degrees C, where we were able to look up the Henry's law constant of our tetrachlorophenol here, and we want to correct it down to 25 degrees C. And we've been told to assume that the delta HAW is 70 kilojoules per mole. So we remember this equation from the Henry's law constant lecture. Because we're using the dimensionless Henry's law constant here, we have to use this form of the equation where we have this little RT average term. Okay? So sometimes it's easier to do this in bits and pieces. So 1 over T1, let's say that because we're going to calculate the Henry's law constant at T2. So T2 is going to be 5 degrees C. T1 is going to be 25 degrees C. So it's going to be 1 over 273.15 plus, here's my plus, 25 degrees Celsius. And then 1 over T2 is going to be 1 divided by 273.15 plus 5 degrees Celsius. So there's my T1 and T2. Just to be explicit, let's put T1 and T2 down here. So this is 273.15 plus 25 Oops. And then this is same thing, except now plus only 5 degrees. Okay, so there's that. So just to be explicit, our T average, you can do this a couple of different ways. We could use the average function here. It's the average of these two temperatures. R, of course, is our friend, 8.314 joules per mole Kelvin. This, by the way, is in Kelvin. Got to keep track of our units. These are all in Kelvin. Okay, so then we have our delta H. So we're going to calculate ln K2 divided by K1. That's going to be equal to our delta H AW, which is 70 kilojoules per mole, times 1,000 to convert units, plus R times T average. Okay, so that's all going to go in one big parentheses, divided by 8.314. Okay, and then this whole thing, again, get our parentheses right, is going to be multiplied by 1 over T1 minus 1 over T2. Oops, no, that's not right. Try that again. Multiplied by 1 over T1 minus 1 over T2. Okay, so then we could EXP that. So that will just give us K2 divided by K1 is EXP of this. So that tells us that the Henry's law constant has dropped so that it's only 12% of its former value, right? So to get the Henry's law constant, KW at 5 degrees Celsius, which is our K2, we're going to take this and multiply it by K1. So now this is our dimensionless Henry's law constant at 5 degrees Celsius. And if we've done all of our math right, we should be able to just copy this over. Now the difference here is that the delta H for Henry's law for aniline is now only 50 kilojoules per mole instead of 70. And we know those should all be right. That should be right. That's all right. And we're using the correct Henry's law constant for aniline at 25 degrees C, and we're multiplying that by this ratio, so we have our new Henry's law constant. You notice, look at that. They're almost the same. Go figure, right? Rene Schwarzenbach, he's so clever. Clever. He's trying to make you do this, and you notice that the pKa's are similar, right, for tetrachlorophenol and for aniline, and the Henry's law constants are similar. So the big difference is that this, my friend, is a base, whereas the phenol here is an acid. Okay, so now we've calculated our new Henry's law constants. Now we want to calculate our DAW, our distribution coefficients. Now, through the magic of television, I have made these equations magically appear. So our distribution coefficient for a compound that's an acid is just alpha times the Henry's law constant. And this is just, the Henry's law constant with units divided by RT, so this right here would be the dimensionless Henry's law constant. So in other words, all we have to do is multiply this value times alpha to get DAW. But the question then becomes, what is alpha? So alpha is going to be our good friend. We remember this from the previous problem we just did. Alpha is calculated like so. So here's alpha. For an acid, alpha represents the fraction of the chemical that is in the neutral form. Right? So alpha is equal to 1 divided by parentheses 1 plus 10 to the power of, I'm going to put some parentheses in here, pH, which we're going to have to put, let's do this a little bit differently. Move alpha over here and make this our pH. 2, 2.5, 3, 3.5. And we wanted to go up to a pH of 7. Zoom, zoom, zoom. Okay, so now our alpha is equal to 1 divided by 1 plus 10. Oops. Yeah, got it. 10. I can do this. There we go. 10 to the parentheses pH, which is here, minus pKa, which is up here. And notice that we're assuming that the pKa does not change as a function of temperature, which is probably a reasonable assumption. So B16 here, we're going to use F4 to put dollar signs in front of it. And now we can bada bing, bada boom, voila. Okay, so now we can calculate our DAW at all of these different pHs, and DAW is just alpha times the Henry's law constant. Bada bing, bada boom, F4. Copy this down. So there's our DAW. And then we want to plot the speciation. So that's the fraction that's in the aqueous phase here. So here's FW. That's going to be equal to 1 divided by parentheses 1 plus DAW here times our ratio of air to water, which is up here somewhere, 10 to the minus fifth, or 10 to the plus fifth, excuse me. And of course this, again, we'll get some dollar signs in front of it. And we can, this is in scientific notation, which is maybe not terrifically helpful, might be more useful to put these in parentheses. Now, our fraction that's in the aqueous phase is pretty low when we're at low pH, but gets much higher when we get to higher pH. So at low pH, we have plenty of protons around to protonate this chemical, to protonate the phenol, and the protonated form of this phenol is neutral, and therefore can volatilize into the atmosphere. So 63% of it is now in the atmosphere. But as the pH goes up and becomes more basic, you pull off the proton. This chemical is now in the anion form, and the anion cannot volatilize. So you see how the distribution coefficient goes down. It's gone down by almost 2 orders of magnitude here, and now 96% of the chemical is in the aqueous phase. So we can do the same thing here for the base. I'm just going to copy some of this same math because it's, no point in doing it all over again. So I'm just going to copy this whole table over here. So our alpha, now to get the fraction that's in the neutral form, we'd have to calculate 1 minus alpha. And to calculate our distribution coefficient, we take 1 minus alpha times our Henry's law constant. So really what we want to calculate here is 1 minus alpha. So that's easy enough. We'll just put some parentheses on this whole thing. And then do 1 minus that. And then we just want to check and make sure that we're using the right values here. B16 is the pKa of the wrong compound. We want to drag that over here so we're using the pKa of the aniline. Otherwise, this formula appears correct. Copy it down. So our DAW now, again, we want to use the Henry's law constant of the correct chemical. Copy that down. This is just the DAW times the ratio of the air and the water, so that doesn't change. So these are all correct. So in contrast to the acid, which was mostly in the water phase at high pH and mostly in the gas phase at low pH, the base is the opposite, right? When it's very acidic around, we have lots of protons around, and so the aniline group here gets protonated. Oops. The aniline gets protonated. So this becomes, the whole thing becomes positively charged, and a positively charged chemical can't volatilize into the air, so virtually 100% of it is going to be in the water phase at these very acidic pHs. But when the pH becomes more neutral, or in this case more basic than it was, 7 is neutral, but it's more basic than 2. So when you get more basic, you're pulling off the proton, you're leaving the aniline in its neutral form. The neutral form can volatilize, and so you have a much smaller fraction now in the aqueous phase. All right, that's problem 8.2.